Good day to you. This is Galactic, bringing you our next presentation in the Unimetrics series, which is simply the application of spherical geometry to problems that are facing physics right now. We have a task at hand, which is to systematize this geometric approach, but in general, this is quite a human field of endeavor, which goes to really some deep philosophical and even religious possible sources of motivation. Because when you're talking about reality and the universe, we're accustomed to doing that now, but that is an extraordinarily recent development that we're able to philosophize more or less in tune with physics. It used to be that they were somewhat distinct necessarily, and it remains so to this day for fairly obvious reasons. But in the case of the entire race of humans looking for answers, well, that goes well beyond science of any kind. This only really comes out when there is no clear answer. For instance, just to bring up a random example, in the case of natural selection, nobody had really ever thought of that before, and so it was doubtful whether it was true, because it was certainly a philosophical change of venue for Darwin to suggest what he did. In fact, why are we considering quantum mechanics at all if our primary interest is astronomy? I'm vastly interested in knowing if the Big Bang Theory has any credibility at all. I've had this somewhat rare opportunity. I need to understand light propagation in order to get at the redshift. And to speak frankly, the Big Bang itself is not really provable or disprovable. But what results from that is a model of the universe. It's assumed that the Big Bang is true, which is neither good nor bad. It's merely a logical extrapolation on the data. There have been, I'll just say, tentative or alternate theories that conflict with the pure Big Bang model. But the model has been reinforced, really self-reinforced. But then what happens is you start getting a forced interpretation of new data. Even though dark matter is quite an ad hoc interpretation, it was felt that it was forced. And all that being to say that we're not really certain if we're deriving an idea of dark matter for a very good reason. It seems to be ad hoc. In order to make the model work, it can be shown that that group effect kind of runs away with itself due to just dynamics that are only insufficiently understood on how humans consensualize scientific information. You would expect something would go kind of fuzzy, at the very least, in trying to penetrate to the core of things. It's like we did expect to find the atom. We've expected that since the time of the Greeks. But once we found the atom, we really weren't fully prepared for what we found inside, where the electron seems to be primarily responsible for the production of light, although it's not restricted to the electron. Protons are known to emit gamma rays. High-speed proton collisions will release the energy that's bound inside the proton, which has, of course, been the focus of study with cyclotrons, and then later they were renamed to hadron colliders after the standard model of particle physics was finalized in their own eyes. I have a couple of presentations on that subject because it is important to know how to get rid of that, because everyone who looks at the standard model of particle physics is appalled. It goes back to the adage, there's always more to be learned. There is the possibility of making a discovery. But in the case of the quantum paradox, it's obvious that there's something fundamentally wrong in our approach. We would have to suspect that our numbers may not be able to cope with the finer and finer granularity of what we're trying to measure. But where it becomes virtually existentially significant is trying to interpret what we already know according to what we see. And you know there's been a bifurcation there. It's when you're going on a linear path and you expect it to continue linearly, but it bifurcates. so that now there are two realities. That's why there is talk of a split universe. And it's because our tried and true linear evaluation system has split. And it splits to wave particle. Extraordinarily difficult to measure. And now we've come to the stage where we're able to do entanglement experiments. Is when John S. Bell published his legendary inequality theorem. After the debate, which resulted more or less in a standoff between the Bohr interpretation and the Einstein interpretation of the phenomena themselves, this became a major metaphysical and even philosophical issue as to who was right. And it was obvious that we can't shake this, that we actually have to understand this, because what we're seeing violates relativity. The general relativity, of course, being macro scale. The quantum paradox is extremely broad-based. So the quantum and the particle and the linear number are all very closely related on one of the most fundamental principles of physics ever brought out by science, which is the fundamental dichotomy between the notion of continuity and the notion of indivisibility. Indivisibility pertains to the particle, and trying to define what you mean by indivisible turns out to be a major issue related to the notion of continuity, which is even more difficult to define because it has no gaps, whereas quanta have gaps. Well, if quanta have gaps, then the gaps are real. It's that gap that we just cannot penetrate. But I found out there is a way to penetrate further, to get further into the quantum, which would obviously be to get further into the quantum paradox, what makes the quantum paradox a paradox. In order to understand that fully, you have to accept space-time, because the only violation that's occurring in the entanglement experiments and double slit experiment and polarization experiments, all of which show violation of Bell's inequality, relativity violating. That's only true if you accept the metric of space-time, because it's in the space-time construction that you eventually find the bifurcation. And that's what I discovered, was the bifurcation. But it's like Pandora's box, releasing what we've been wanting to get, which is the truth. The one who gets the solution to the quantum paradox will be the one who can decide and be able to prove why it violates relativity, because it actually doesn't. And the reason is strange. It's because relativity is causing the violation. It's relativity that causes the quantum perception of something being violated. The experiments done after John S. Bell showed that there's an experimental approach to this whole question of violation of special relativity, is really what it is, that you could actually test it. And then, as you know, the Nobel Prize in Physics was awarded just the year before last for what was merely the latest series of progressive proof that special relativity is indeed violated. I consider that to have been proved. I don't see how so much effort could have gone into that research, which is the most, or I'll just say certainly at the highest level of excruciating exactitude to do the entanglement experiment. It's almost inconceivable that it could be done when it's described what has to be done, which is worth a quick review. When the two particles are put into a coordinated state, they're said to be entangled, because when you separate them, you can then test them to see if they remain entangled. And if they do remain entangled, you can prove that they have remained entangled by taking a measurement on one of them and then measuring the other one before light can propagate that distance. That's why they always tend to say, in promoting this to the public, the excitement behind all this, they'll say those two particles could be on opposite sides of the universe, or they could be on opposite sides of the solar system. I think you see why that would be said. A grotesque overstatement and a complete bald-faced lie. That's an extremely localized phenomenon. And those particles could never, those two particles cannot be separated, such that you could measure perfectly the violation of special relativity. And nobody is sure, even now, whether that has actually been shown. It's that serious and delicate and difficult. But all of the motivation now is skewed due to bias. And it's hard to decide who's biased. I had to face this at every turn in trying to deconvolve the mystery of this paradox, even to describe how it is known to be a paradox. So that's our introduction today to a later presentation on the absolute data-oriented, structure-oriented definition of the geometry that I am using, spherical geometry, to explore these issues from a brand new perspective. Certainly, at the very least, it would have to be said that a spherical perspective on it, I have proved that that is the only way to explain the quantum paradox. I can prove that there's no other explanation. You must switch to spherical geometry to understand light speed, space-time, the speed of light, and the quantum paradox, and the electron-proton relationship, and the force balance of centripetal and centrifugal force that define universal force balance. This will change our perception of gravity, and this will get at the problems in the cosmology that's currently accepted, because they're based on things that can be shown to have been ad hoc, and that will tear down their model. Their model is incorrect, but the solution is in geometry, and nobody could see the connection because the new spherical geometry is an extension of the linear number system into a two-fraction unit component reciprocal number system that replaces linear algebra. No more calculus, no more sine cosine, no more complex numbers. That alone would be incentive enough to look further into this geometry. But the geometry explains the Boschkovich force curve. So I hope you're enticed. I hope you stay tuned. The next few lectures are going to be quite data-oriented and structure-oriented, and I'm going to have visual, mostly text and diagrams that I've composed. These are the formulas, these are the constants, these are the equations, these are the transformers, these are the objects, in one bolt. This geometry has the potential to revolutionize a lot. So I hope you stay tuned, keep looking up. That's where you're going to find your solutions. Once you know everything else, you still need to look at the universe, because that's what you're trying to understand. That's what I'm doing it for. All right, stay tuned. We'll be right back. This is Anagalactic.